At its core, antenna polarization refers to the physical orientation of the radio wave's electrical field as it travels through the space. When an alternating current is applied to an antenna, it generates an electromagnetic wave consisting of two components, an electric field, E field, and a magnetic field, H field. These two fields always travel perpendicular to each other and perpendicular to the direction of propagation. The orientation of the E field dictates the antenna's polarization. Most standard antennas are linearly polarized, meaning the electric field stays in a single plane. The polarization is determined by how the elements are mounted relative to the earth. Horizontal polarization. If you string up a wire dipole parallel to the ground, like a standard 80 meter or 160 meter dipole, the electric field oscillates horizontally. This is the standard for most HF dexing and terrestrial weak signal VHF UHF work. It tends to pick up less man-made electrical noise, which is heavily vertically polarized. If the antenna elements stand straight up, the electric field oscillates vertically. This is standard for local repeater work, mobile setups, and AM broadcast stations. It provides an excellent omnidirectional ground wave. Circular polarization. Instead of staying in a single flat plane, the electric and magnetic fields rotate continuously in a corkscrew pattern as they travel. Right-hand circular polarization and left-hand circular polarization, depending on the phase relationship of the driven elements, the wave spins clockwise or counterclockwise. Why it is used? Circular polarization is vital for LEO, that is low Earth orbit satellite operations. Because a satellite is tumbling through space, its antenna orientation is constantly changing relative to your position on the ground. If you try to track a tumbling satellite with a linearly polarized antenna, like a standard handheld Moxon or Yagi, you will experience severe rhythmic signal fading, spin fading. A circularly polarized antenna like a cross Yagi ensures you maintain a consistent link regardless of the satellite's physical orientation. Cross polarization loss. For line of sight communications, the transmitting and receiving antennas must have matching polarization. If you try to receive a vertically polarized signal with a horizontally polarized antenna or vice versa, the theoretical signal loss is infinite. In the real world, due to scattering and reflection, this cross polarization loss is typically around 20 to 30 dB. That is enough to make a perfectly readable signal completely disappear into the noise flow. Here is a demo. Here is a visualization of cross polarization losses. As the misalignment angle increases, you can see that the loss will also increase. Now the angle is 38 degrees and the loss is minus 2.2 decibels. The visualizations are seen here. Transmitting antenna and the receiving antenna are getting cross polarized gradually. Now it is 87 degrees, almost perpendicular to each other, minus 23.1 decibels. Now as the angle increases, this is lower. You can see the difference. 180 degrees, there is no difference. So the maximum loss is occurring at 90 degrees cross polarization. You can see here. It's almost 90 degrees, 89 degrees. It is minus 29 dB loss. This is the maximum cross polarization loss. The sky wave exception. When you are working HF and bouncing signals off the ionosphere, Polarization matters much less on the receiving end. The ionosphere heavily refracts and scatters the wave, a phenomenon called Faraday rotation, effectively scrambling the polarization. A signal transmitted horizontally might arrive elliptically or vertically polarized. This is why you can successfully work a DX station using a vertical antenna even if they are transmitting on a horizontal dipole.